Welcome to Educator.com. In today's session, we're going to talk about several special functions. The first one we're going to discuss is the step function. And a step function makes a unique looking graph. It's a function that is constant for different intervals of real numbers. And the result is a graph that is a series of horizontal line segments. So they look like steps. And that's where the name step function comes from. Best way to understand this is through an example. So, for example, if apples were sold at a price of $1 per pound, okay? So apples sold at $1 per pound. And the price is such that you're charged $1 for each pound or any part of a pound. In other words, they round up in order to determine the price. So if you had 1.5 pounds of apples, they're going to charge you $1 for the pound and then another $1 for the half pound. So they charge you $1 for a pound, and then any part of a pound is considered a full pound in terms of pricing. So if X is the number of pounds and Y is the cost, then let's see what kind of values we get and what the graph looks like. Okay, if I have 0.8 pounds, I'm going to get charged $1. They're going to round up. If I have a full pound, I'm going to get charged $1. If I have a little bit over a pound, I have 1.2 pounds, I'm going to get charged $1 for that first pound, and then the 0.2, it's going to be another $1. So $2. 1.4 pounds, again, $2. And on up, 2 pounds, $1 for the first pound, $1 for the second pound. 2.5. $2, and then the 0.5 is another $1, so that bumps me up to $3. Until I hit 3 pounds, it's $3 also. 3.8, $3 for $1 for the first pound, $1 for the second pound, $1 for the third pound, another $1 for that 0.8, so $4. So you can see that the function is constant for different intervals. So for this first interval, from a little bit above 0 all the way to 1, the Y value is constant. It's $1. For the next interval, which is just above 1 all the way to 2, including 2, it's going to be $2. Once I get above 2, up to and including 3, it's $3, and so on. So this is constant for different intervals of real numbers. Looking at what the graph looks like, any part of a pound up to and including $1 for that first pound is $1. Now, 0 pounds of apples are going to be $0. So I'm not going to include 0, but even, 0.1, slightest part of a pound is going to be $1. So I put an open circle to indicate that 0 is not included, but just above that is, all the way up to and including 1. Since 1 is included, 1 is also $1, I'm going to put that as a closed circle. So here I have pounds. And here I have the cost on the y-axis in dollars. Now, once I get just above 1, let's say 1.1 pounds, they're going to charge me $2. So not including 1, but just above it, so open circle. All the way up to 2. At 2 pounds, I will also be charged $2. Once I hit just above 2, I'm going to be charged $3. All the way to 3 and including 3, and on. So you can see how this looks like a series of steps and how this is a result of the fact that the function is constant for different intervals of x. So this function is the same for this entire interval, then it's the same for the second interval and on. So this is a step function. A second type of function that you'll be working with is an absolute value function. And these functions have special properties. So looking first at f of x equals the absolute value of x, just the simplest case. So x and f of x. And here, f of x is just going to be the absolute value of x. When x is 0, f of x is also 0. When x is 1, absolute value is 1. And so on for positive numbers. Now let's look at negative numbers. For negative 1, absolute value is 1. Negative 2, the absolute value of x is 2. And on. The result is a certain shape of graph. So when x is 0, f of x is 0. X is 1, f of x is 1. X is 2, f of x is 2. And on. Now, for negative numbers, negative 1, f of x is 1. Negative 2, f of x is 2. Negative 3, f of x is 3. And it's going to continue on like that. So absolute value graphs are V-shaped. So we're going to end up with a V-shaped graph. Depending on the function, the graph can be shifted up or it can be shifted to the right or to the left. And let's see how that could happen. Let's now let f of x equal the absolute value. So here f of x equals the absolute value of x. Let's say f of x equals the absolute value of x plus 1. Okay, so we're given x and the absolute value of x is 0, but we're adding 1 to that. So this is going to become 1. Absolute value of x is 1. 1 plus 1 is 2. 3. 4. Absolute value of negative 1 is 1. 1 plus 1 is 2. Absolute value of negative 2 is 2. Add 1 to that, it's 3. And add 1 to 3, you get 4. Okay, so it's the same as this, except increased by 1. Each value of the function has been increased by 1. So now let's see what my graph's going to look like. When x is 0, so right here I have the graph for f of x equals the absolute value of x. Now I'm going to look at this graph. When x is 0, f of x is 1. When x is 1, f of x is 2. When x is 2, f of x is 3. So you can see what's happening. And then here I have x is 3, f of x is 4. Negative values. When x is negative 1, f of x is 2. When x is negative 2, f of x is 3. When f of x is negative 3, f of x is 4. Okay, drawing the line through this. This is the graph of f of x equals the absolute value of x plus 1. So you see that this graph, the V-shaped graph, is simply shifted up by 1. And again, you can also shift this from side to side, and we'll see an example of that later on. So absolute value function, it is very important to find both negative and positive values of the function. So assign x 0, assign it some positive values, and it's very important to find what f of x will be when x is negative. Because if I picked only positive values, I'd end up with half of a graph. So to get the entire V shape, choose negative and positive values for x. The third special function that we're going to discuss is called a piecewise function. And a piecewise function is a function that is described using 2 or more different expressions. The result is a graph that consists of 2 or more pieces. Just starting out with one that consists of 2 pieces. The notation is usually like this, with one large brace on the left. F of x equals x plus 2 for values of x that are less than 3. And f of x equals 2x minus 3 for values of x that are greater than or equal to 3. So you see that for different intervals of the domain, the function is defined differently. So it's a function that is described using 2 or more different expressions. So for the part of the domain where x is less than 3, this is the function. For the interval of the domain that is greater than or equal to 3, this is the function that I'm going to use. Let's see what happens. Let's first use this part of the function where f of x or y equals x plus 2. And for the domain, remember that x is going to be less than 3. So I'll go ahead and start with 2. When x is 2, f of x or y is 4. When x is 1, so I've got to remain at x value is less than 3. When x is 1, f of x is 3. When x is 0, f of x is 2. Just picking a negative number. When x is negative 4, f of x is negative 2. I'm going to graph that here. Okay. When x is 2, f of x or y is 4. X is 1, y is 3. X is 0, y is 2. X is negative 4, y is negative 2. Okay. Now, this is for values of x that are less than 3. So 3 is about here. Therefore, anything just below 3, but not including 3, is going to be part of this graph. So we're going to use an open circle here to indicate that 3 is not going to be included as part of this function, the domain for this function. So it's going to begin at just below 3 and continue on indefinitely. That's the first piece of the graph. The second piece of the graph is for x such that x is greater than or equal to 3. And here, y is going to be 2x minus 3. So greater than or equal to 3. So I'm going to first let x equal 3. 3 times 2 is 6, minus 3 is 3. Getting larger, when x is 4, that's 2 times 4 is 8, minus 3 is 5. When x is 5, 5 times 2 is 10, minus 3 is 7. Okay. Now, this does include 3, this section of the graph, this piece. So when x is 3, y is 3, right here. When x is 4, y is 5. So x is 4, y is 5, right here. When x is 5, let me shift that over just a bit. When x is 4, y is 5, right here. When x is 5, y is 7. Okay. Now, if you look, this actually did end up including all possible values of x, all real numbers, because when x is less than 3, I use this function. And then as soon as x becomes 3 or greater, I shift to this other function. So you can see how there are 2 pieces to the graph. And you actually can have situations where there's more than 2. You could be given, say, f of x is 4x plus 3, 2x plus 7, and x minus 1, and then given limits on the domain for each of those. So at least 2 pieces, however, there can be more. In example 1, we have a greatest integer function. Before we start working on this, let's just review what we mean by the greatest integer function. So when you see this notation with the brackets, let's say that you have a number in here, such as 4.7. What this is saying is that this value is equal to the greatest integer that is less than or equal to 4.7. So that's 4. So it's the greatest integer less than or equal to whatever's in here. If it was 2.8, it would be 2. Be careful with negative numbers. Let's say I have negative 3.2. The temptation is to say, oh, that's equal to negative 3. But if you look at it on the number line, 3.2 is right about here, negative 3.2. Okay? So if I have negative 3.2 and I'm trying to find the greatest integer that is less than or equal to 3.2, it's going to have to be something over here, smaller. So it's actually going to be negative 4. So just be careful when you're working with negative numbers. Whatever's inside here, whatever that value is, you're going to find the function is equal to the greatest integer that is less than or equal to this value in here. Understanding that, you can then find the graph. So let's find a bunch of points for this so we make sure we know what's going to happen with various situations. When x is 0, this inside here is going to be 2. The greatest integer less than or equal to 2 is 2. When x is 0.6, then you're going to get 2.6 in here. The greatest integer less than or equal to 2.6 is 2. 0.8, I get 2.8. Again, I round down to 2. All right, so when I hit 1, 1 plus 2 is 3, and the greatest integer less than or equal to 3 is 3. Slightly above 1, that's going to give me 1.2 plus 2 is 3.2. The greatest integer less than or equal to 3.2 is also 3. Okay, so you can get the idea of what this is going to look like. And that continues on. And then when we hit 2, 2 plus 2 is 4. Greatest integer is going to be 4. For negative numbers, let's take negative 0.5. Negative 0.5 and 2 is 1.5. So 1.5, the greatest integer less than or equal to 1.5 is going to be 1. Now notice I have a negative number for x, but this did not come out to be a negative number. So that's different than the case I was discussing there. Let's go a little bit bigger. Let's say negative 3. Negative 3 and 2 is negative 1. And that's going to be negative 1. Let's say I take negative 3.5. Negative 3.5 and 2 is going to equal negative 1.5. Again, just thinking about that to make sure you have it straight. If I have negative 1.5, so I have 0, I have negative 1, I have negative 1.5, I have negative 2. The greatest integer less than or equal to this is actually negative 2. Okay. Now plotting this out. When x is 0, f of x is 2. When x is slightly above 0, it's 0.6, f of x is 2. 0.8, it's 2. So all the way up until I hit 1. At 1, f of x becomes 3. Therefore, 1 is not included in this interval. So you can already see that this is going to be a step function because we have intervals. For different intervals of the domain, we have that same value for the range. All right. For values between 1 and 2, f of x will be 3. Once we hit 2, I got to do an open circle because 2, the value for f of x jumps up to 4. Okay, so you can see what this is going to look like, and that pattern is just going to continue. Let's look over here at negative numbers. So when x is slightly less than 0, then you're going to end up with an f of x that is 1. So for values slightly less than 0, but not including 0, this is what you're going to end up with. Okay, looking, say, when x is negative 3. When x is negative 3, f of x will be negative 1. But when we go slightly bigger than that, or slightly more negative, when x is negative 3.5, f of x is going to be negative 2. It's going to be down here. So the steps on this side are actually going to have the open circle on the right. Then I'm going to jump down, and it's not going to include negative 2 because negative 2 and 2 is 0. So negative 2 is going to be right here for the x value, and the f of x will be 0. But as soon as I get to a little bit bigger than negative 2, the greatest integer is going to be down here. Okay? And so we continue on like that with the steps. And you can see how this is a step function. So you just have to be very careful and pick multiple points until you can see the pattern, where for a certain interval of the domain, the range is a particular value. Okay, so that was a step function, and it involved the greatest integer function. Example 2, now we're working with absolute value. G of x equals the absolute value of x minus 3. And we already know that the shape of this graph is going to be in a V. But we don't know exactly where that V is going to land. So let's plot it out. When x is 0, the absolute value of x is 0, minus 3, that gives me negative 3. When x is 1, the absolute value is 1, minus 3, so g of x is negative 2. When x is 2, absolute value is 2, minus 3 is going to give me negative 1. Now let's pick some negative numbers for x, because that's really important to do with an absolute value graph. When x is negative 1, the absolute value is 1, minus 3 gives me negative 2. You can already see my V shape is going to occur. When x is negative 2, the absolute value is 2, minus 3 is negative 1. Absolute value of negative 3 is 3, minus 3 is 0. So this is enough to go ahead and plot. X is 0, g of x is negative 3. X is 1, g of x is negative 2. X is 2, g of x is negative 1. Over here with the negative values, when x is negative 1, g of x is negative 2. When x is negative 2, g of x is negative 3. When x is negative 3, g of x is 0. So you can see that I've got a V-shaped graph. And compared with my graph that would look like this, that would have the V starting right here, it's actually shifted down by 3. So that's an absolute value function. Here you can see that you're given a piecewise function because there are two different pieces. And this could also be written in this notation. So there's two different sections to the graph, and we see that the function is defined differently for different intervals of the domain. Starting with if x is greater than 2. So x, and this is going to be for x values where x is greater than 2, f of x is going to be x plus 1. So when x is 3, f of x is 4. When x is 4, f of x is 5. When x is 5, f of x is 6. Okay. So when x is 3, f of x is 4. When x is 4, f of x is 5. And it's going to go on up. And that's going to go all the way until just greater than 2. 2 is not going to be included on this graph because it's a strict inequality. So I'm going to use an open circle. And this is going to continue on. Now, for x less than or equal to 2, I've got a different situation. I'm looking at f of x is negative 2x. Okay, so when x is 2, 2 times negative 2 is negative 4. When x is 1, 1 times negative 2 is negative 2. When x is 0, f of x is 0. When x is negative 2, that's negative 2 times negative 2 is positive 4. So starting with x is 2. When x is 2, f of x is negative 4. And that is including the 2. When x is 1, so these are values greater than or equal to 2. Less than or equal to 2. So I'm getting smaller, less than or equal to 2. When x is 1, f of x is negative 2. X is 0, f of x is also 0. When x is negative 2, f of x is up here at 4. Okay, so I've got a steep line going right through here. So you can see this is a piecewise function consisting of two pieces, and here one picks up where the other leaves off. For values greater than or equal to 2, this is my graph. For values of x less than or equal to 2, this is my graph. So that was a piecewise function. Okay, this time in example 4, we have both greatest integer and absolute value in this function. Recall that for the greatest integer function, what that's saying is that whatever's inside this bracket, let's say it's 1.2. It's asking for the greatest integer less than or equal to 1.2. In that case, this would be 1. Or if I had 4.8, it would be 4. For negative numbers, like negative 3.2, the greatest integer less than or equal to negative 3.2 is negative 4. Okay. Now, since this is a bit complicated, it is helpful just to take it in stages. So I'm going to look first at what the greatest integer of x is, and then I'm going to look for the absolute value of what that is. If x is 0.2, the greatest integer less than or equal to 0.2 is 0. The absolute value of 0 is 0. So this is the function that we're looking for. And the same would hold true of 0.5. Round down to 0, absolute value 0. When we hit 1, the greatest integer less than or equal to 1 is 1. Okay, and the absolute value of that is 1. 1.2, again, we're going to go down to the greatest integer that's less than or equal to 1.2, which is 1, and the absolute value is 1. Same for 1.8, and all the way up until 2. Once we hit 2, the greatest integer less than or equal to 2 is 2, absolute value is 2. So that's working with positive numbers, greatest integer and the absolute value, it's the same. Okay, so let's go to negative. Negative 0.4, the greatest integer that is less than or equal to negative 0.4. So I'm looking and I've got 0 and 1 and negative 1, and negative 0.4 is about here. So I'm going to go down to negative 1. The absolute value of that is 1. Here you can see that the greatest integer is not the same as absolute value. Or for negative 1, greatest integer less than or equal to negative 1 is negative 1. The absolute value is 1. Negative 1.8. Greatest integer that's less than or equal to negative 1.8. I'm going to go down to negative 2, and the absolute value is 2. For negative 2, the greatest integer less than or equal to negative 2 is negative 2. The absolute value is 2. So you see that there are intervals here. Intervals of the domain end up with the same value for the function. So I'm going to have a step function. But remember that absolute value graphs are usually V-shaped. So I'm actually going to end up with a V-shaped step function. Let's plot these out. So for 0, the absolute value of 0, the greatest integer of 0 will be 0, and then the absolute value will be 0. So with 0, we're going to include it. And for all values up to but not including 1, the function is going to equal 0. Once we get to 1, I have an open circle because it's not included. When x is 1, f of x is 1. So I'm going to jump up here. All the values between 1 and 2, but not including 2, will have an f of x, or a y value, that is 1. As soon as I hit 2, open circle, I'm going to jump up. And this is going to, once I hit 2, f of x is 2. All the way up to, but not including 3. And it's going to go on that way. And you see now we have the step function and that it's V-shaped like absolute value. Let's look over here on the negative side of things. So for negative 0.4, so somewhere in here, it's going to equal 1. Negative 1 is also equal to 1. So here on the left side, I actually have a closed circle and an open circle on the right. It's the opposite of what I had over here. When I get to less than -1, my value for f of x is going to jump up to 2. So this is closed circle. I get slightly less than, but not including -1. It's going to jump up to 2. -2, my value is also 2, and everything in between. And then when I get to just slightly more negative than -2, like -2.1, it's going to jump up to 3. So you can see how this is V-shaped, and it's a step function. The step function comes from it being a greatest integer function. The V-shape comes from that absolute value. And you also just had to, be careful how you're doing the open and the closed circles. Okay.